I am Anil Kumar. Welcome to my series on calculus. We'll learn about limits. Here is our lesson number 2 on limits. In lesson 1, we learned about the basic concepts of limits. Now, we'll look into strategies to evaluate limits. Along with this video, we have a number of videos on YouTube which can help you practice, and also I can provide you with examples from previous test papers that can prepare you for your own examination. We are going to complete the unit on limits with just 3 videos. One which was our lesson number 1, providing introduction. This one here, we'll learn the strategies to evaluate limits. And in the third lesson, we'll see how to attempt an examination question paper. So let's begin with the strategies which we need to understand to evaluate limits. Now, I've written here a trigonometric function, limit x approaches 0 for sine ax over sine bx. And also provided with your graph, which is of a similar trigonometric function. Now, we'll look into strategies which can help us find limits for many other functions, not just a trigonometric function. We'll begin with the very basic ones so that we build upon a concept and becomes simpler for us to explore this particular idea of evaluating limits. Some of the limits could be evaluated by direct substitution, and that is indeed the easiest and the best way to do it. So as I was saying, direct substitution is definitely the best way of working with, but most of the questions cannot be answered by direct substitution. So you may get a form which is kind of 0 over 0. So when I substitute 0 here, we get sine 0 over sine 0. The units are radians for angle for trigonometric functions. Now that will give you 0 over 0. Now this 0 over 0 is called indeterminate. So if after substitution you get a form which is 0 over 0, there are many similar forms also. It could be infinity over infinity also. It could be infinity minus infinity. So there are different indeterminate forms. So when you get into these indefinite forms, we have to apply different strategies. One of the strategies is to factor. The other one is to simplify. We could even rationalize. We could have change of variables at times, especially when we are dealing with absolute functions. We might like to use one-side limits. So let me write down a note here that if you find absolute functions, in that case, one-side limit is a good approach. We'll also take up examples where we'll find limit as x approaches infinity. So let's begin with the very first example, which is, well, here we have about 11 questions to do. Well, there are 12. So these 12 questions are there before you. We'll see how to solve them one by one. We'll also learn the techniques to solve them as we move along. So I'd like you to actually pause the video at this stage. Look into these questions. You may copy, solve them also, and then check your solution with mine. But my idea here is to understand these strategies. Once we understand all these strategies mentioned, then it'll be very easy for you to solve any question on limits based on such strategies. So question number 1 here is that we have a rational function, right? Limit x approaches minus 2 for this particular rational function. Now, whenever you see this rational function, first thing is you need to substitute minus 2 here. As soon as you substitute minus 2, as I've done here, right, you will see that you don't get 0 over 0. You actually get the value. And this value is minus 2. So that becomes your solution. So by substitution directly, you will get the solution. Now think about it. If you do not do this substitution and then you solve like in a regular fashion, thinking that this is a rational function, the best way is to factor. You might have to factor, and at the end, you might get this answer. But sometimes factoring for such examples, especially in the test papers, might be very difficult. I purposely took a simple one here so that I could easily show you that it could be done by factoring. But many times, factoring a cubic function, you might require additional strategies. Okay, so strategy number one, substitute and then check. If you don't get 0 over 0, then you get the answer, perfect, and that serves. Now we have the second question here, which is very similar. So again, a rational function, a cubic function on the top. Now, we have limit of this rational function where x is approaching half. Now when I substitute half in this particular expression, I get 0 over 0. Well, for x over 2, 1 over 2, we get 0 over 0. What does that really mean? Let's understand this. 0 here means that 8x cubed minus 1 is 0 for x approaching or x equals to half. That means 2x minus 1 is a factor. Similar is the case in the denominator. So if we factor, we could cancel that 2x minus 1 factor and then substitute to get the limit. Perfect. So that's the whole idea. So I've written here in short, this indicates a common factor of 2x minus 1 in the numerator and denominator. Now this is a very important point to appreciate as we move along. Perfect. So now we just factor this particular rational function. You can see the factoring process. 2x minus 1 is definitely a factor which cancels out. And once that cancels out, you substitute half and you get your answer, which is 6 in this particular case. So that becomes the solution for us. Perfect. So we have seen the strategy of factoring. Next one here is limit of 2 to the power of minus 1 minus x to the power of minus 1 over x minus 2. Now that is also a rational function, limit approaching x equals to 2. Now in this particular case, you can clearly see that if I substitute x equals to 2 here, what will happen? As I do x equals to 2, we get 0, especially in the denominator, and in the numerator also you'll get 0 over 0. Now since it is indeterminate, we'll actually continue with simplifying such expressions. So when you get into expressions which are like this, they look very difficult to work with, but they are easy to simplify. So simple steps is we could write this reciprocal of 2, reciprocal of x, which is 1 over x minus 2, and when you simplify, you get a very simple expression which is 1 over 2x. The common factor x minus 2, which was giving you 0 over 0, cancels even in simplification. So sometimes very simple steps to simplify really helps, and we get our answer, which right here is 1 over 4. Remember, in any test paper, 75% of the test paper is based on these techniques. Now, if you learn these techniques, you easily get those 75%, and for next 25%, you might have to do some extra practice along with more examples, which we are getting into, right? So later half, we'll have some more examples which could get you over there. Then I have hundreds of videos in my YouTube which you can watch. Now here is another example. Again, we have a function which needs some strategy. Limit x minus square root 3 over x square minus 3, where x approaches square root of 3. If I substitute square root of 3 for x, I get 0 over 0. Perfect. So that means it is indeterminate. Now whenever you have square root function involved, the best strategy is to rationalize. Perfect. So in this particular case, we'll definitely do rationalization, right? So once you rationalize, it can be simplified. Well, it could also be factored, right? So what I did actually was that I factored it. Since we could also treat x square minus 1 as x square minus square root 3 square, right? So you understand, we have this x square minus 3. We could think it like this, x square minus square root 3 square. Do you see that? Now it becomes a square minus b square. So it can be factored with a plus b times a minus b. So I could write this as x plus square root 3 times x minus square root 3. So that's what I've done at this particular stage. So instead of rationalization, this time I factored it. So what I applied here is this technique of factoring. Perfect. But you could do rationalization also. Perfect. So we'll multiply and divide by x plus square root 3 to get the simplified form. Now let's take the next example here clearly. Once you do this factoring, you find that this common factor x minus 3 and square root 3 cancels. And so you get a term where you could substitute x equals to square root 3, and then after simplification, you get your answer. Now here is another very important thing to understand. Now, some of you could have written this particular answer, right? But square root 3 should not be written in the denominator. So what we have done here is we again rationalized so that we have an answer which is square root 3 over 6. Now that is a very important step. Many times in multiple choice questions we may be provided with the other answer, and so that is how you should get it. Perfect. Let's look into the next example, which is limit cube root of x plus 64 minus 4 over x. Now in this particular case, when I substitute 0, what do I get? I get 0 over 0, right? So that means it is again indeterminate form. Now you could rationalize, that would be very difficult. However, now we will do substitution method. Now substitution is a very important and a powerful tool which can be used in many of the equations, right? So remember, substitution. We'll try to understand how do we actually do it. So first thing is we identify the term which could be simplified after some substitution. So in this particular case, the term cube root of x plus 64 is very difficult. So we'll substitute this with some other variable. We chose u. So we are saying u equals to cube root of x plus 64. So if you cube it, you can say u cube is equals to u cube minus 64 is equals to x, and that can give you the value of x, right? So you could substitute x with u cube minus 64. Perfect. So what we did here was, let me rewrite. So we have u equals to cube root of x plus 64, correct? So that takes care of the numerator. Now in the denominator, we have x. So we need to isolate that. So we could cube both sides and we get x plus 64, and that leads to the value of x as equal to u cube minus 64, correct? So that is what I have written here. Now, this is one part of substitution, right? The other part of substitution is we have to substitute x also, the limit. So when x is approaching 0, what happens to u? Substitute 0 here. So let's figure it out. So what happens to u when x is 0? So we say when x is approaching 0, what happens to u? So u in this case will be cube root of 0 plus 64, which is cube root of 64, which is equal to 4. And that is what I've mentioned here. So when x is approaching 0, when x is approaching 0, u is approaching 4. So now we are in a position to replace each and every part of our original equation. So instead of the limit cube root of x plus 64 minus 4 divided by x, where x approaches 0, we could write it in terms of the new variable u. So u minus 4 over u cube minus 64, where the limit of u approaches 4, becomes a modified question. But it is equivalent question, correct? So we could now simplify this using the formula for factoring a cube minus b cube formula, right? So let me rewrite here the formula of a cube minus b cube, which is equal to a minus b times a square plus ab plus b square. A very important formula which all of you should always remember. So once you apply this formula, it's very easy to factor the denominator and write it as shown here. Now once you write it like this, you can always cancel the common terms. So cancelling them leads to a simplified expression where you could substitute u equals to 4 and get your solution. Perfect. So we get our answer, which is 1 over 48. Is that clear to you? Right. Take a moment to understand the whole process. So remember, first identify the portion which should be substituted. So the complicated part was the cube root of an expression. We substitute that as u. We should also know what is x in terms of u. So you could cube this and isolate x to find the value of x. So this is one part which takes care of the function itself, right? Now, we should also know the limit part of it. When x approaches 0, what happens to u? Substitute x as 0 in the expression and find the value. Then only you're in a position to completely write your expression or the question in terms of the new variable u in this particular case. So I hope that is absolutely clear. So let's continue. Take up the next question, which is evaluate. And the question here is limit absolute value of x plus 4 divided by x plus 4 where x approaches minus 4. Immediately substitute x equals to minus 4. You could do it in your mind also, right? So you get 0 over 0 for x equals to minus 4. That means it is indeterminate form. So we have to apply some strategy. Whenever it comes to absolute functions, let me write it clearly here. So whenever you're looking into absolute functions, then the strategy which you should think about is write absolute value as a piecewise function, right? So we have absolute function, you write it as piecewise function. So when you have two pieces, then you have to approach from the left side and from the right side. And that is what I say when I say apply or solve by one side limit, right? So that means clearly you have to split your domain into two portions at least and then work from both the sides. Now the limit will exist if the limit from both the sides is equal. So that's what we have done here. So we have first defined our absolute function. The absolute function x plus 4 should be written as minus of x plus 4 when x is less than minus 4. But it is positive value when x is greater than minus 4. So we have now two intervals to work with. Perfect. When we are working on the interval of x less than minus 4, we are actually trying to find limit from the left side, right? So that is our left side. So we have written limit of x when x approaches minus 4 from negative, I should write, from the left side. And the expression from the left side is minus of x plus 4 divided by x plus 4 when they cancel actually, leading to minus 1. So minus 1 is the limit on the left side. On the right side, we have to write plus here. This is the right side limit. Now, you can clearly see we got plus 1 here and minus 1. Now, left side and the right side limits are not equal, so the limit does not exist. You get the idea. So you have to mention that both the limits are not equal. One is negative, the other one is positive. They are not equal. Therefore, the limit does not exist. Perfect. So there could be many examples where the limit may not exist. I hope the steps are absolutely clear. So whenever you find an absolute function in the case of limits, it's a good idea to actually write it as a piecewise function and then solve. This strategy actually works for solving equations and inequalities in terms of absolute functions also. The next question here is question number 7. So midway, we have actually seen all our strategies and how they work. Perfect. Now, we have some extra practice for you. This will help you to actually achieve better. So I'd like you to pause the video now, apply the strategies as we see the question, and then check with my solution. Question number 7 is to find the limit of x to the power of 4 minus 1 divided by x minus 1 when x approaches 1. As soon as I substitute 1, I get 0 over 0, indeterminate form. So the best strategy in this case should be what? Well, clearly it is factoring. So you could apply the factoring concept, a square minus b squared, right? Which is a plus b times a minus b. Remember, to factor it fully, right? So you get the first step, but see, this expression can be further factored, and there you go. So once you do that, in that case, you do get a common factor which can be cancelled. So you get a simplified expression substituting x equals to 1. And this simplified fraction expression gives you the answer, which is 4. The next question here is, we will now find limit when x approaches infinity. Now these are very important questions. I'd like you to pause the video, focus on, and then we'll move forward. We need to find the limit of square root of x squared plus x where x approaches infinity. And this is minus infinity, right? So we are saying x approaches minus infinity. Perfect. Now, it is also an indeterminate form. Can you tell me why? Well, if I substitute minus infinity here, minus infinity square becomes a very large positive value, and so square root is infinitely large, right? So the first portion is infinitely large, right? Now, since we are working with this particular function, which is x is approaching minus infinity, this value, when substituted with minus infinity, will give you minus infinity. So we have minus infinity, infinity minus infinity. It could give you a real value, right? So large value, take away large value. It could give you, right? It is possible, a real value. So it is indeterminate. However, limit, because we need not be there, the limit could be real, can approach a value L, and that is what we're trying to figure out. You understand? So that is another form of an indeterminate form. We have already seen two forms earlier, which is 0 over 0, or we could have infinity over infinity. Now we're looking at the third form, which is infinity minus infinity, right? These are very important things to understand. Another important concept to understand as we move along is, what is square root of x squared? Now that's a very important question. You could watch my videos on this. You can search for Anil Kumar square root of x squared to look into the solution. Well, square root of x squared is not x. Many students think that square root of x squared is equal to x. Now this is incorrect. It is absolute value of x. You understand why? Let me take an example here. If I have minus 7, right? Minus 7 is the value of x. Now if I square this and if I square root this, what do I get? I get square root of 49, which is equal to 7. Remember, it is not minus 7. It is actually equal to the absolute value of 7. You get the idea. Perfect. This is the most important concept. Now, if you do not understand this concept, then all your questions based on such principles will be wrong. And definitely, this is the question which can help you get more than 90% marks, right? So, here is the question. Perfect. So, that's what I was saying. Till now, whatever we have done takes you to around 75% in this test paper. Now the questions we are building on one by one every 5%. Perfect. So here you go. You are above 90% if you could solve this question without any problems, right? So let's begin. So in this case, we have square root. And we have indeterminate form, infinity minus infinity, and that could be real. Therefore, we'll try the technique of rationalization and see how. We have done the rationalization where only we have a kind of numerator, right? Denominator is 1 for this particular function. So you rationalize by its conjugate as shown here, multiplying and dividing by the conjugate, and then simplifying. Now in simplification, here is a very critical step. So as soon as you come to this particular portion, you have this difference of squares, right? And the denominator is that particular thing. Now x squared minus x squared cancels, and you're left with x in the top. The denominator here is square root. Let's look into this denominator part, which is right there. What we did was we factored x squared. When you factor x square, you get 1 here, right? And plus x divided by x square, which is 1 over x minus x. Now, the simplification for this written here is absolute value of x minus x. How did I get there? Can you tell me that? Well, if we're looking into the limit when x is approaching negative infinity, then this is approaching 0, right? It is 1 over x. So this portion is approaching 0. So when this approaches 0, we're left with only x square here within the square root. And what is square root of x square? Square root of x square is equal to absolute value of x, and that is what I've mentioned. Is that clear to you? Correct? So that is what is this particular step. Now, second step is again a very critical step. Now, what is absolute value of x? I wrote minus x. Well, how come? Big question, big time. Now let's try to understand this also. If I'm defining the absolute value of x, I could write this as minus of x or plus of x, depending on where am I going. So if I am saying x is less than 0, it is minus x. But when x is greater than 0, then it is plus x. Since we are approaching minus infinity, we have to write this as minus x. Is that clear to you? Again, we are approaching x towards minus infinity, and therefore this implies that absolute value of x should be taken as minus x. That is a piecewise function, and that is how the pieces are. Does it make sense to you? Now I'm emphasizing on this for a reason, since many times this concept is not understood, and therefore this question normally is unanswered. It is never answered. I have not seen test papers with correct answer of this particular solution so far. Perfect, except for those students who have been my students and they know this technique. Okay, now clearly it is minus x now. Perfect, it is not 0 in the denominator as some of you might get. Okay, so we land up with minus 2x in the denominator. Do you see this portion? And then you can directly simplify and you get minus half as your answer of this particular question. Most important question amongst the 12 which I have taken in this particular video. I hope that makes sense. So let's move forward. You can revisit this particular portion and then understand the technique. But for now, let's move forward. And another question is here, which is limit square root of 7 minus x minus 2 divided by 1 minus square root of 4 minus x, where x approaches 3. How are you going to solve this? Big time. Now, what I do here is, let me substitute 0 here, 3 here first. So when I write square root of 7 minus 3 minus 2 over 1 minus square root of 4 minus 3, what do we get? 7 minus 3 is 4, square root of 4 is 2, right? So we get 2 minus 2 here. Here we get 1, 4 minus 3 is 1, 1 minus 1. So we do get 0 over 0. So definitely this is indeterminate form. Now, some of the students do not realize there could be rationalization with both numerator and denominator. So this particular question, we have to rationalize both numerator and denominator. So the numerator has been rationalized with the conjugate square root 7 minus x plus 2 divided by square root 7 minus x plus 2, and also by the denominator conjugate as shown here. So that's a critical step to watch and understand, right? That takes you to 95% of your learning on limits. Okay? Now, you could easily now simplify this, and once you do that rationalization, other steps are not so difficult. So you get this kind of a result, right? And then you just substitute the value of x minus 3, and you get your answer, which is minus half. Perfect. So go through these steps, have a good look at it so that you could capture the information. The whole idea of typing it out now clearly and putting it on a yellow background is for you to capture the information and retain. So I hope you got it. Let's move forward and see how to do the next question. Well, here we have a question which is very commonly seen in the test papers. We have limit square root of x minus 1 divided by cube root of x minus 1 where x approaches 1. How are you going to do it? Now, there are many techniques to do it. However, the method of substitution is probably the best. But what should you substitute by? Is it square root of x equals to u? Is it cube root of x equals to u? What should it be? Now let's think about it. We have two different values here. We're talking about x to the power of half, that is square root of x, correct? And we are also talking about the cube root, which is x to the power of 1 over 3. We want something which could take care of both. So what could that be? You get the idea, right? So we have to see the common factor, right? So we're dealing with this and we are dealing with this. So the idea is we can only work with this if we have a common denominator, and that is 6. So basically look for the lowest common denominator, right? So that helps you while working with fractions. So you could add or subtract fractions only when you have a common denominator. It makes sense, right? So that is what is key here. And therefore, we have a substitution which is x equals to u to the power of 6. Do you see that? Or x to the power of 1 over 6 is u. That is the substitution which I have done. Perfect. So if x is equals to u to the power of 6, then x to the power of half will be u to the power of 6 by 2, which is u cubed, right? And x to the power of 1 over 3 will be u to the power of 6 by 3 or u squared. You get it? That is how you have to do the substitution. Once you do that, then you get all this. Correct? So we substituted x as u to the power of 6, and then we figure out what is square root of x. Square root of x is u cubed, and the cube root of x is u squared. So we can now replace the expression whose limit we need to find. We have the function now in terms of u. Now we have to look into the limit part of it. When x approaches 1, what happens to u? U also approaches 1. So we'll change the limit part to u approaches 1 and rewrite this particular question in terms of u as shown here. Remember also to change the limit to u. Perfect. And then continue using the expression limit u approaches 1 till the end. Now, once you write it in terms of u, we have a cubic difference and then we have a quadratic difference of squares in the denominator. Now, this could be factored with the known formulas which we have already come across. And as you can see here, you could actually simplify since u minus 1 is a common factor. Once you take care of this particular factor, the simplified expression, you can substitute the value of u as 1 and get the answer, which is 3 over 2. So that is a very important question to take you more than 95%. Now rest 5% is always luck, a bonus. So we'll try some other questions. We'll go slightly beyond, and we have been working in Calculus 1 Part 1, where at present I'm just introducing you to trigonometric functions, as that could be a tricky part at times. So you could also get questions based on trigonometric functions. Well, later on, once we do a part of more derivatives, we'll get to details about how to find limits for trigonometric functions, exponential and logarithmic functions. But at present, we are only touching upon that so that you get in concept as we go along. So here is question number 11 for you, which is find the limit of sine ax divided by sine bx where x approaches 0. Now we already learned in our previous lesson, lesson number 1 on limits, that the limit of sine x over x is 1. So when you learn some concept, I would like you to make a note of these concepts. So that becomes kind of a formula for you. So those of you who missed my first lesson, well, here is what we did. So basically, we have this particular function here, limit of sine x over x when x approaches from the left side, sine x over x when x approaches from the right side. So we just substituted the values as we approached, and we got a value which was very close to 1, right? And so we could conclude that from both the sides, it is 1. Remember, units, angle in radians. Is that clear to you? So that is how we get our formula, right? So remember these formulas as we move along. The idea is to use them, apply them, and then get solution to new questions based on these formulas, right? So here, you need to apply the formula, which is limit sine x over x when x approaches 0 equals to 1. And that should help you to get the answer. Okay, so what can we do? We have the term sine ax, correct? Now, when I say sine x over x, somehow we have to substitute something, right? Or what we could do here is we could just multiply this by the term ax over ax, correct? So in that case, we can rewrite this as sine of ax over ax times ax. Perfect, does make sense. So what we do, we bring this there. And so we have this particular expression, right? So let me rewrite the next one, which is sine of bx. So when we have sine of bx, I could multiply and divide by bx over bx. Do you see that? So I wrote it directly so that you understand that we could find this particular limit. We know it's like a theta, right? It is the same thing. So we could think about one particular argument, which is bx. And this portion, the limit of this, we can apply the formula and write this as 1. That's the key part, right? So, and then we have in numerator and denominator the terms ax and bx, in which the x will cancel and we'll get our answer, which is a over b. Perfect. So that is the strategy to solve such questions. Now look at the solution here. So we have sine ax over sine bx where limit x approaches 0. We know we can apply this particular formula provided we get some x there in the denominator, which is basically the argument, right? So we want ax here in the denominator, so we multiply and divide by ax over ax. And the same thing is done for the denominator also. Rearrange. Once you rearrange, then you could actually get a term which could be like this. Now at this stage, moving from here to there, we have also used properties of limits. Clear? Now, actually speaking, when we have this ax over x, we should first cancel away x. Since x is not depend now, since a over b is not dependent on x, we could take it outside, right? So it should be taken outside after canceling. So I should have cancelled x from here. You get the idea. So we have the term a over b, which is independent of x, so we could take the limits inside. So what, that is the reason. Do you understand? So this term a over b is independent of x. And then you can take it outside. So you cancel first. Then do the next step, okay? So it is a mistake here. Okay. Now you know the limit of this particular function and also the numerator, it is 1. So basically it will be this times 1 over 1, and so you get an answer which is a over b. So we get this answer as a over b. Is that clear to you? Now there could be many questions based on this concept. It is a very simple concept and therefore it is there in the test paper even if you're not really working with trigonometric functions. I hope this point is clear, right? Okay, let's take the next question, which is again a trigonometric function for us. You need to evaluate the limit sine of cos x divided by cos of sine x when limit x approaches 0. You know one formula so far about the limits of trigonometric functions. Sine x over x, the limit x approaches 0 is 1. Okay, now here we could actually directly substitute. So when you do substitution, let me write down substitute x equals to 0. What do you get? So when you substitute x equals to 0, you get cos 0 and sine 0, right? So those are the x values. So what is cos 0? Cos 0 is 1 and sine 0 is 0. And what is sine 1? Sine 1 is a number, right? It's a real number, right? So that is a real number. 1 is in radians, right? 1 in radians. And we know cos 0 is 1, right? We know cos 0 equals to 1. So we get sine 1 as our answer. So in this case, the answer is sine 1. Is that clear to you? Radians, we'll normally write with C on the top. So I could have written C on the top here, mentioning 1 is radian. But by default, unit is radians for trigonometric functions. So if you don't write, it is radian. It's just a ratio. So that works. This brings us to the end of our video. Now here is a very important learning. So I'll actually like you to also revisit the beginning of our calculus lecture. So when we did introduction to calculus, at that time we have worked with this formula, which is E is a limit of 1 plus x to the power of 1 over x when x approaches 0. And we actually found that limit by approaching from the left side and from the right side, substituting the value of x which were approaching 0, as you can see here. And from both the sides, we came up with 2.7184, perfect answer for 4 decimal places. And we know E has this answer. But that brings us to another important concept which is relevant now. So when you substitute 0 here, so what do I get? I get 1 plus 0 to the power of 1 over 0. So it is basically of the form 1 over infinitely large value. Now that is indeterminate form. Why? You say 1 over anything is 1? But it is 1 over infinitely large value. Will it be 1? That's a big question, correct? We have seen it's kind of different, right? When we worked out, it came out to be 2.7184, right? It is not 1. So it was an indeterminate form, correct? Now the same question we could have in the form of x approaching infinity, right? And that is the limit. Let me write here limit. And the expression could be 1 plus 1 over x to the power of x, correct? In that case, we get 1 plus 1 over infinitely large value over infinity. Now, this is 0, so we get 1 over infinity again. So both are similar forms. So the fourth form of infinity is 1 over infinity. So to conclude, the indeterminants basically have 4 different forms. Okay, that's kind of important to understand. So we began with our lesson right here. In this, I'll conclude by saying that you normally should directly substitute and check your result. But then when you do the substitution, you get indeterminate forms. So what are these indeterminate forms? You could have 0 over 0, right? You could have infinity over infinity, as we have seen. You could have infinity minus infinity. You could have 1 over infinity. Do you understand? So at least 4 we have seen in this particular case. There are other forms also which could be derived from here, but at least 4 are known to you, right? So at least 4 you know. Now, we will actually look into this later when we look into L'Hopital's rule. So after derivatives. Is that clear to you? So we are going to revisit this particular unit once we understand derivatives, and then I will use here L'Hopital's rule. And we'll come with more functions which will be more trigonometric, exponential, and log. Right? So we'll add that to our vocabulary soon after doing derivatives, right? So we're going to revisit this and learn to how to find limits, and in between, we'll also look into squeeze theorem. So I'll treat that as an advanced level of Calculus 1, which may be of interest to some of the students. But this is the basic Calculus 1, which most students will need, especially for GCSE level A. This should be sufficient. So with this, we kind of end our learning about limits, and the next session we'll take up examination style questions to practice. I hope you find it interesting and useful. I recommend you to go through my playlist to practice, practice, and practice so that you are absolutely ready. 100%. Perfect. Thanks for your time and all the best.